This Zoom session is being brought to you by the Fractal Globe Snow Ring, W. Today, this is a juicy one. I like this section, although it's kind of hard to do and hard to grade, because here the problem is that the answers don't consist of yes or no or 17 or whatever. This actually requires you actually do proofs. And that means you write a sort of an essay. And this is a math course, not an essay course, except for this. Okay. Mathematical induction is one of the more ingenious methods of mathematical proof. And it's a little subtle. So I'm going to take a little more time than usual over this time. First of all, the name is kind of inaccurate. Mathematical induction. Induction is compared to deduction. Deduction is the act of reasoning from the general to the specific. All men are mortal. Socrates is a man, therefore Socrates is mortal. You start with general principles and yield specific results. Okay, it's completely certain, but it is no more, but it gains no more information than was originally given to you. Induction is the process of reasoning from the specific to the general. So every morning you've seen the sun rise in the east, therefore the sun rises in the east. This is pretty good. This is science, although it should be said that in the Arctic regions, the sun spins around in the sky all day for 6 days a year. That's 6 months a year. So induction is more creative, but less certain. Mathematical induction is really a form of deduction, but it does include observing a specific case as part of how it works. You can think of mathematical induction as sort of like how if you line up a row of dominoes and you tip over the first one, then eventually they all fall down. Mathematical induction is kind of like that. It's trying to prove a proposition P of n true for all n. So for all n, property P holds for n. Here's how it works. You make two assumptions and deduce that P is always true for all n. You start for saying that P of 1 is true, that number 1 has property P. That's called the initial case. Then the next step is a little subtle and you have to be careful. It says you assume that P is true for the counting number K. And from that, you deduce that it's true for the next number, P of K plus 1. So you start by assuming that P is true for 1. You then assume that then you prove that if it's true for K, then it's true for the next number K plus 1. And from these two, you deduce that P is true for all n, because it's true for 1, therefore for 2, therefore for 3, therefore for 4, therefore for 5, therefore for 6, and so on forever. Now that forever implies that there's a little bit of infinity inside this mathematical induction, which gives it a little bit of uncertainty. But okay, it is a fundamental principle of modern math. Now, like I say, I don't really like the name mathematical induction, although that seems to be, we're stuck with it. I prefer than to call it reasoning by recurrence, but whatever. All right. Now, okay, here's a classic. You have a first n even numbers, 2 plus 4 plus 6, all the way up to 2n. Add them, and you get n times n plus 1. Prove that. Prove that's true for all n. All right. A lot of series proofs go by mathematical induction. And okay, first, we start for the initial case. We set n equals 1. Well, left side will just be 2, and the right side will be 1 times 1 plus 1. Also 2. So it checks. So the initial case is confirmed. Now, here comes the induction step. And like I said, it always seems a little suspicious because you sort of assume your theorem, at least for case K, and then from that prove it's true for case K plus 1. And it's almost like assuming what you're trying to prove. So it's you have to be a little careful with it. Okay, you assume that it's true for K. 2 plus 4 plus all the way up to 2K. That equals K times K plus 1. We assume that. All right, well, let's find, is it true for the next case? Well, we take the first series and add 2 times K plus 1. That'll be the left side for K plus 1. Well, we're assuming this is equal to K times K plus 1. Then we have K times K plus 1 plus twice K plus 1. Okay, well, what do you know? Common factor of K plus 1, pull it out. I'm leaving K plus 2. And so you get, and this will rewrite as K plus 1 times K plus 1 plus 1. Ah, well, this is the statement of the theorem for K plus 1. So assuming the statement true for k means that it's true for k plus 1, and that confirms the induction step. The statement is the identity is true for 1. The induction step is confirmed as well, so it is therefore true for all n. The sum of the first n odd numbers up to 2n, and even numbers up to 2n equals n times n plus 1 for all n. This is now proved. Now, in the homework, I will want you to write something like this, an actual small essay. I realize this is harder than what was done before. Please do not hand in a page on a page saying true. I know it's true. I want you to prove that it's true. This is, however, a little unlike the problems I've had so far where I was content with the answer. Here, I'll be requiring an actual proof, or at least something close to a proof. Here's a cube one. Sum of the first cubes, n cubes, 1 cubed plus 2 cubed all the way up to n cubed equals n squared times n plus 1 squared over 4. This is pretty heavy, I think. Sum of cubes equals n squared n plus 1 squared over 4. Well, okay, first we'll start with the initial case. Let's try n equals 1. And the left side is 1 cubed. The right side is 1 squared times 1 plus 1 squared over 4. The left side is 1. The right side is 1 times 2 squared over 4, which is 4/4. Check. All right, fine. So the initial case is in fact confirmed. Excuse me, this seems a little flawed. 3, 1. That looks like a 4 there. That's not good. All right, now we'll go for the induction step. We assume that the series equation is true for value k. Let us prove it for k plus 1. So the sum of 1 cubed plus 2 cubed all the way to k cubed equals k squared times k plus 1 squared over 4. Looks good. Well, then, okay, we add the next term, k plus 1 cubed. So we'll take this, k squared, k plus 1 squared over 4, and add k plus 1 cubed. Well, okay, on this right side, this term and this term has a k plus 1 squared in common. Okay, so pulling out that k plus 1 squared from each of these two terms, this term becomes k squared over 4. This becomes k plus 1, simple enough. I'll rewrite this, I'll putting it all over 4. K squared plus 4k plus 4 over 4. Okay, sounds good. And k squared plus 4k plus 4 is the square of k plus 2. Looks good. And so I get k plus 1 squared here. K plus 2 squared is k plus 1 plus 1. So that's squared over, and all that over 4. And this, for this to equal this, is the statement of the theorem for the value k plus 1. So from assuming it true for k proves that it's true for k plus 1. So the induction step is confirmed. Therefore, the formula is proved for all n, all counting numbers n. This is true for all positive whole numbers. Okay. Here's a general formula. N is less than 2 to the n for all counting numbers. Okay, let's prove that. It's true for n equals 1. You put n equal 1 here and 1 here, you get 1 less than 2, which is true. So the initial step is confirmed. Now let's assume that k is less than 2 to the k. And okay, then let's look at k plus 1. Well, that'll be, well, okay, that'll be less than twice k. Okay, for n, less than or equal to twice k. And adding 1 to a number will only double it for k equals 1, less than double it for everything else. And twice k will be twice this, twice 2 to the k. And 2 times 2 to the k is 2 to the k plus 1. Therefore, k plus 1 is less than 2 to the k plus 1. And we've confirmed the induction step. Therefore, the theorem is true and is always less than 2 to the n for all counting numbers. Well, okay, that's the method of mathematical induction. It is, like I say, a little tricky because the induction steps, you sort of have to assume what you're trying to prove and then prove from that assumption that's even more true. So beware of this subtlety. But okay, these are the problems in the homework for section 8.5. So there you have it. Okay, I think we're done for now. All right. Darling, I see your chat. I'm glad you're here. I pity about your technical difficulties. I hope you overcome them soon. We have done our section for today. What's left in the book is 8.6, talking about, what is it again? Oh yes, the binomial theorem. A very nice theorem. We'll be seeing that later on next Monday. Then we'll have some a week or so of review and so on. I'll be here to receive all questions. And I believe the homework is ready. Let me double check that. Have I opened up the homework set, the final yet? Let's find out. Because I figure it's about.
I don't believe so yet.
Well, let's do it now. All right. Your homeworks are there. Oh, there it is. You're right. I haven't opened it up yet. Well, voila, it's now open for you. Okay. You have till I guess the 16th or maybe the 17th, I dare say, for you to get all that back to me. You know the routine. Write it up, scan it, send it into the inbox. And I'll send it back. And I'll send back my grades, the corresponding grades accordingly. Okay. Whoops, I thought I'd stopped recording.